Today's section is 1.1 and let it be limits and uniform convergence. You may ask about example from former lecture. Remember, I didn't finish it, but I decided to continue later after this new material to reconsider that example together with extra information which can be added with the help of today's material. So, the question is the following. Look, what do we want to do? So we know there is a limit of a fan of x, which is equal to, let's say, f of x. And we know there is a limit as x tends to x naught, f of x equal to an. The question is, when limit as x tends to x naught, f of x equals to the limit so we have two limit processes. One as x tends to x naught in argument of the function, and another limit process when n naught. And the question is if we can change the limiting process, because if you substitute, look, f of x is this limit, an is that limit. So that means we ask about the possibility to change limits. You see, the question is when we can interchange the order of two limits. So in general it is not possible to do, so maybe I will give some example. Yeah, I will give an example later. But it turns out that uniform convergence guarantees the possibility to change the order of two limits. And that is one of several explanations why uniform convergence is important. Because otherwise, you cannot guarantee such a simple thing like just to change limits. Okay, so theorem 1. Limit of uniformly convergent suppose that the sequence fn of x converges to f of x uniformly on E x naught is a limit point of E for each and in natural there exists the limit as x tends to x naught x in E of fn of x. Let it be equal to a. Then there exists the limit as x tends to x naught x in E of f of x. There exist in fact two limits. Limit as n tends to infinity of n, and they are equal. So we can interchange limits, in fact, and because of uniform continuity. No, because of uniform convergence. Proof. So I'll start with using uniform convergence. So Fn converges uniformly. What is the limit after this? Here, limit is x tends to x naught, x in E. Here, the same. X tends to x naught, x in E. The same. The same. This is same as that one. So Fn converges to F uniformly on E. Then by Cauchy criterion of uniform convergence, what we can deduce? For arbitrary epsilon greater than 0, there exists natural number capital N, such that for all n greater than capital N, for all natural E, for all x in E, we have inequality Fn plus E of x minus Fn of x less than x. Okay. Now, look at the last part of this graph. So, what is written here? For arbitrary x, we have such uniform graph. And what we know? We know there exists for each n natural, there exists the limit of Fn of x as x tends to x naught. X naught. So, for a moment, I'll fix everything else. epsilon, capital M, little m, p, everything is fixed. We look only at the very last part. So, the very last part is valid for all features, little m, p, and epsilon, right? For all x. And I know there exists a limit on this line, fn plus q of x, as x tends to x. So, what I do? Take a limit as x tends to x naught, x in q, right? Come on. X tends to x naught, x tends to x is in q, right? What happens then? Then, as we know, there exists limit, right? Which is denoted by a n. So here I have a n plus b, there a n. Right? And we know properties of inequalities. If we have an inequality, then we can take a limit and we preserve the sign of inequality up to equality, right? So might be no free up there. So what we deduce, I'll rewrite all other quantifiers without change them. And what remains now? Modulo a n plus t minus a n less or equal to but what it means? What it means? What is written here? It means that the sequence a n by definition is a Cauchy sequence. This is a Cauchy sequence, right? And we know that every Cauchy sequence has a limit. So there exists a limit as n tends to infinity and n equals to, let's say, so there exists a limit. I denote it by n, right? So one thing is true. There exists such a limit, right? But we need to check other things, and for that reason, what we have to consider. Look, so now I want to use once again that Fn tends to F uniformly on E. Arbitrary epsilon equal to 0. There exists capital N such that for all n greater than this n, we have for all x in E, we have Fn of x minus f of x less than, okay, I think epsilon over 3 now. And now look, here it is written arbitrary, little n greater than capital. So fix n. Then epsilon is arbitrary, right? So I choose arbitrary epsilon positive. For this epsilon, we found capital N, right? And now I fix at least one of those little n. I need only one. Okay, then look. Limit for this n, limit as x tends to x naught, x in E, fn of x equals to an. We know what it means. For our epsilon, remember, I fixed it, right? So they exist. That is greater than 0 by definition of the limit. Such that for all x in E, which satisfy the inequality 0 less x minus x naught less than delta, we have an equality fn of x minus an less than epsilon over n. And in fact, I should fix n sufficiently large. Not only like that, but also, I'm sorry, I forget to mention it. So now I know limit an equals to a, right? Hence, I can choose n such that an minus a less than epsilon over b. So this n should be also sufficiently large to have this inequality. So when I said fix n, we fix n which is sufficiently large to satisfy both inequalities, that one and this. Now, look. So, for arbitrary epsilon greater than 0, we have found delta positive such that for all x in E satisfying this inequality, I can write the following chain of inequalities. F of x minus a is less or equal f of x minus f n of x plus f n of x minus a n plus a n minus a, where I choose same fixed n equal to n. And now look, every term here is less than epsilon over 3, right? So the sum is less than epsilon, and now look. What is underlined is precisely the definition that limit as x tends to x naught, x in E, f of x equals to a. So simultaneously we have proved the existence of this limit and the fact that they, right? The theorem is proved. The theorem is proved. Okay. Now a corollary. if Fn converge to F uniformly on E and Fn are continuous on E, then F is continuous on Okay, let's prove it. How? Prove for the carbon. First case, x naught is not a limit point of E. A limit point of E. Or what's the same, x naught is an isolated. Then we don't need to prove anything. Why? Because we know that if a function is defined on a set and x naught is an isolated point of this set, then automatically the function is continuous. Because we cannot approach to x naught, right? So it's sufficient to have a function which is definite somehow, and that's all. Okay. So here we don't need to prove anything. And if x naught is a limit point, then continuity of Fn at x naught is equivalent to say that the limit as x tends to x naught, x in E, Fn of x equals to Fn at x naught. That is by definition of continuity at a limit. So continuity means that the limit equals to the predicate of the function at this point. And then apply theory, right? So uniform convergence we have, right? X naught limit point, we have limits. So instead of an, we have Fn of x naught. So by theorem 1, we deduce that the limit as x tends to x naught, x in E of f of x equals to the limit as n tends to infinity, Fn at x naught. And we know the sequence Fn converges to f, right? So we know this is precisely f at x naught because of the definition of f. F is a limit, is the limit of the sequence Fn. And you see that is precisely continuity. So f is continuous at x naught. And analogous assertions are valid for functional series, because uniform convergence of functional series is equivalent by definition to uniform convergence of the sequence of partial sums. So theorem, let's say 1 prime, if the series sum n from 1 up to infinity f n of x converges uniformly on E and Fn are continuous on E, then the sum f of x equals to the sum of f of x is continuous on E. So, for the proof, line corollary to the sequence of partial sums as n of x equals to the sum k from 1 to n fk of x. So finite sums, they are continuous for sure, and it means we have a limit of a sequence, uniform convergence sequence, so everything works. Okay, now how it can be applied. So, example 1, and in fact it is a continuation of the last example of former lecture. So, example 1. And consider this former lectures. And for alpha greater than 1, the series converges uniformly on R by Weierstrass test. We did it yesterday. So it was section 20.2 yesterday. And now let me add new information. So by theorem 1 prime, okay, Sine x over n alpha are continuous on R. Hence, by theorem 1 prime, the sum of our series Sine x over n bar alpha is continuous on R. So that is how the theorem works. You see, we cannot write down the value of this infinite sum explicitly. It's difficult, and I would say it's impossible to write it down explicitly. But nevertheless, we know some properties of that function. That is a function of x. That is a function of x. And we know that this function is continuous. So, without knowledge of the function itself, nevertheless, we can learn some properties of that function. That is very important. Okay, let's continue now our example. And in fact, that is a good example to use Dirichlet test. What we did, in fact, when we considered convergence of series, we did it. So practically, I plan to do this one. Same consideration. And we will modify slightly. So, for the second part, I want to apply Dirichlet test. Test for uniform convergence of series. And we take n of x equals to sine x, dn of x, and power up. So for Dirichlet test, we have two suppositions to be verified. So we have to verify two suppositions. Which supposition? The first one is partial sums of our sine x should be uniformly bound somewhere. Uniformly bound on E. We don't know yet what is about the set. Okay, and the second is that the sequence n power alpha is monotone and uniformly converges to 0 on E. The last supposition is very easy to check. Why? Because look, alpha positive it's true, right? Why? If I'm sorry, but the n of x n power minus, right? Because 1 over n, right? N power minus. Why it is true for alpha positive? We have n power minus, right? When alpha is positive, n power minus alpha, that's true, right? And uniformly on E, why? Because it doesn't depend on x, right? What means uniformly? It means that you can put quantifier for all x in E after the quantifier exists. But you can put it everywhere, right? Because it doesn't depend on x at all. So definitely everything is valid for all x because we have no x. So it doesn't depend on x. So that is satisfied automatically, and it's quite usual. So when you have something which does not depend on x, then once you have a property, let's say boundedness, convergence, then it is automatically
uniform because of absence of. If you have no x, then your property is very uniform. Automatically. Okay, let's carry it. Now, we checked the second supposition, right? Or the differential tests. Now, what's about the first? Here, what we do, we proceed. Let me recall how we did it for usual convergence. We take sine x over 2 and we multiply and divide with this sine x over 2. Then what we will obtain 1 over sine x over 2. Here we have 2 here, cosine of the difference and minus 1 half x minus cosine of the sum x, sorry, capital N here. And then that is precisely what is it? Cosine x over 2 minus cosine n plus 1 over 2 n plus 1 x over 2 sine x over 2. And now we can estimate it as follows. So let's say equals 2 over 2 modulo sine x over 2. And for example, if we suppose x is in the interval from delta to 2 pi minus delta, right? Then what we will obtain that x over 2 belongs to delta over 2 pi minus delta over 2. And then, by properties of sine, what can we say about sine? So look how we define sine. So x over 2 is an angle from delta over 2 up to pi minus delta, right? Sine is ordinate of this angle, so sine is ordinate which varies somewhere here, and it means sine x over 2 is for sure directly equal than sine delta over 2. Right? That is minimum value of the ordinate. So if we have arbitrary angle between delta over 2 and pi minus delta over 2, then the ordinate of a point, corresponding point of the unit circle, is greater equal than sine delta over 2. So we can estimate 1 over sine delta over 2, and that is valid for this. So that is our set E, which is not defined yet, but now it's a good point to define. So what it means? It means that for arbitrary, so what we obtain by Dirichlet test, so the result is that the series Sine and x over n power alpha converges uniformly on the interval delta 2 pi minus delta for arbitrary delta positive. Okay, delta let it be 0 pi, right? It makes no sense to make delta greater because nothing between. And alpha positive. So that is what we can deduce by using Dirichlet test. Okay. Uniform convergence on such an interval. And apply now theorem 1 prime, what we obtained at the sine continues. The continuous function on delta 2 pi minus delta. For any delta in 0 pi and for any alpha positive. And now very popular way to deduce facts about continuity. Look. Formally, we have continuity on arbitrary closed interval from delta up to 2 pi minus delta, right? Where delta is arbitrary constant. Because of arbitrary, we deduce that our function is continuous on 0 to pi. Well, because take arbitrary point here in open interval, then you can find sufficiently small delta, so x naught, let me draw a picture, right? 0 to pi. Take arbitrary x naught, right? Then you can find delta sufficiently small such that delta is here, right? Delta is here. And you have continuity on this interval, and it means in particular the function is continuous at x. So the function is continuous at arbitrary point of the interval 0. Okay, to complete the former example, so look, at the moment, what we know? We have uniform continuity, uniform convergence on the whole real line for alpha greater than 1. We have uniform convergence on such a closed interval for arbitrary delta and for arbitrary alpha positive. And the question is, what's about alpha non-positive? What's about uniform convergence for non-positive? And also about uniform, what's about uniform convergence on the whole interval 0 to pi. Here also. So, third point, the series Sine x over n power alpha doesn't converge uniformly on, let's say, 0 to pi. So you see, we cannot replace delta by 0. That's impossible. For alpha from 1 up to, sorry, from 0 up to 1, from 0 up to 1. How to prove it? We use Cauchy criteria. In fact, we have not so many tools to prove the absence of uniform convergence. Namely, we have Cauchy criterion, negation of Cauchy criterion, and also negation of term test for uniform convergence. And here, of course, term test doesn't give absence of uniform convergence. So, negation of Cauchy criterion. So there exists epsilon greater than 0, such that for all capital N natural, there exists n greater than capital N, there exists P natural, there exists X 0 to pi, such that the sum k from n plus 1 up to n plus p sine kx over k power alpha is greater or equal than x. That is what negation of Cauchy criterion says. Okay. And you see, we need to find sufficiently large and an arbitrary p. And it's rather often to choose p equals to n. Of course, I cannot explain why it works. Fortunately, in many cases. So you see, there exists p, right? And it turns out that the simplest way, and that is, I would say, simplest way to choose. Look, so term test doesn't work to prove the absence of uniform convergence. Why? Because, look, if you consider one term tends to 0, sine is bounded by 1, right? And 1 over n power alpha, for alpha positive tends to 0, right? The general term tends to 0. That is why you cannot expect to have here p bounded. It's impossible. For sure, you have to choose something to obtain here more and more terms. So p should tend to infinity. And the simplest way to choose something what tends to infinity is just to take p equals to n. Okay? Then, look, next point. So, I want to estimate now this, in fact, p equals to n, so I have just 2n, right? I want to estimate somehow such sum from below. So to estimate below, right? To estimate below. And so I have kx, look, where is it? Greater equal greater nx, less or equal to nx, right? So I would choose x. Let it be, let's say, pi over 4n. Then what we will say? Look. What is it? So kx is between those, right? And what we deduce from here? Kx, what is n times x? Pi over 4, right? And less or equal pi over 2. So look, we consider sum of this pi, right? K starts from n plus 1 up to n. And once I choose x, remember, I have to choose one x for all k which are here, right? I cannot choose different x's for different terms. It's impossible. I have to choose one value of x for all terms in our sum, right? Then look, kx for our, in fact, for arbitrary positive x, right? If k starts from n plus 1 and terminates at to n, then what happens with kx? It is between nx and 2nx, right? And if we substitute our value of x, then we deduce the following restrictions for kx. And if kx is from pi over 4 up to pi over 2, then what can we say about sine kx? It is greater than sine of pi over 4. What is 1 over square root of 2, right? Because of properties of sine, right? Then I can estimate, look. So now I know all values of sine kx are positive, so I can write just the equality of this. Then that is greater 1 over square root of 2. And then look, okay, firstly let me write the sum. Then 1 over k power alpha. Now let me estimate in that way. Look. So I want to have an estimate below. The question, we choose p equals to n because we want the sum to tend to infinity. In fact, you will see it need not to tend to infinity. No. I want to have infinity, the number of terms tends to infinity. Number of terms tends to infinity. You see, number of terms in that sum tends to infinity. That's important. the total value of sum need not to be infinite. We'll see. But the number of terms here tends to infinity, right? Because number of terms is p, and p equals to n, so it tends to infinity. So we have more and more terms. Okay? Tends to infinity, not infinity. Yeah. Okay, now look. I want to find estimate below, right? Alpha is positive. So that is greater or equal minimal value when I will substitute maximum value of k, right? Maximum value of k is 2n. So I have, let me write like that, greater or equal 1 over square root of 2 times 1 over 2n power alpha. I wrote minimal term, right? So I replace every term of our sum by minimum term. And then how many terms we have? We have precisely n terms, right? So I should multiply by n. And now look. We have n to the power which power? 1 minus alpha, right? And we suppose alpha is less or equal than 1. So n power alpha, 1 minus alpha is greater or equal than 1, right? So you see that in fact, if alpha equals to 1, then the result is does not tend to infinity. We have infinitely many terms in the whole sum, but we need to estimate somehow. That's the point. You cannot estimate infinitely many terms. Why? Because sine, values of sine, they oscillate. Plus, minus. That is difficult, right? You need to estimate the sum below. But for that reason, you need to be able to control values of sine. That's how we proceed. So number of terms tends to infinity, but what's important, we can control values of sine for all those things. Yeah, you see, that's important. So we need to go between two restrictions, right? One of them, we want to have many terms. Another, we need to control somehow values of sine. That's important. So we vary between those restrictions. Okay. So, you see, there is always for arbitrary alpha from 0 to 1, right? And in particular, it means that we have here an estimate 1 over 2 power alpha plus 1 half. But that is a positive number, right? For sure. Positive number, and that is precisely epsilon, which I can indicate now, right? So we have found a positive value of epsilon, such that. So you see that in fact here it was necessary to find for arbitrary capital n a greater little n. And in fact, what we did, we proved it for all little n, right? Doesn't matter which n we choose, doesn't matter. We proved even more. But the point is that somehow we estimated the sum at a point x doesn't tend to 0, and it means indeed our sum does not converge uniformly on the whole closed interval 0 to 1. That is how to do with uniform convergence. And in fact, for alpha less or equal to 0, we don't need to proceed with uniform convergence. Why? So for alpha less or equal to 0, the series diverges for x not equals to phi k. We did it before when we considered series, and if we haven't even convergence, then for sure we haven't uniform convergence as well, right? So, and of course, we cannot ask about, what are reasons why we consider uniform convergence, why we want to prove it? That is to prove that the function is continuous. That is why we consider, right? And if the series diverges, then what's about continuity? No function, it is not defined, right? So it makes no sense to talk about uniform convergence in this case. Okay, that is for this example. Now, more examples, simple examples. Example 2. Okay. Fn of x equals to 1 over n x plus 1. So, look, let's consider x in 0, 1. What happens then? So, first case, x in such an interval which is open from one side, right? If x is not 0, then what can we say about limit as n tends to infinity of n? What is it? You see, x is not 0, n goes to infinity, so nx plus 1 tends to infinity, and the result is 0, right? 0. But for x equals to 0, all fn of x are equal to what? 1, right? Hence, the limit fn of 0 is 1 as well, right? So, it means that we have the following result. 0 for x, 1, x equals to 0. And that is precisely f of x, the limit function. What's about properties of that function f of x? Is not continuous on 0, 1. And what we can deduce now using theory 1 prime. Look, if fn are continuous functions, right? If fn tends to f uniformly on the closed interval 0, 1, then the limit function should be continuous, right? According to theorem 1 prime. Uniform convergence of a sequence of continuous functions implies continuity of the limiting function. So, uniform convergence would imply continuity of f on 0, 1, but f is not continuous. Hence, what can we deduce? Fn does not converge uniformly to f on 0, 1, right? So we don't need to consider separately uniform continuity here, just to refer to properties of uniformly convergent sequences. So if the limit is not continuous on a set, then for sure we haven't uniform convergence on this set. Okay, and in fact, next topic which I want to consider is related to integration of series. And as a preparatory examples, let us consider, so example 3, fn of x n squared, fn of x n squared x 1 minus x squared power n. X on 0, 1. So, what I want to consider now is, okay, in fact, what's about time, what I can do. Okay. Yeah, from one side, what's about pointwise limit? Look, if we take x from 0 to 1, exclude 0, right? Then what do we have? 1 minus x squared is strictly less than 1, right? Hence, the limit is 0. Moreover, we considered such a limit if a greater than 1 and k is arbitrary. So a is 1 over 1 minus x squared. So a is greater than 1. And k equals to 2, right? So it means the limit is 0 of fn of x. For all x from 0 to 1 excluded to 0, but in fact what happens to 0? Because of that x is for sure 0, right? So we have limiting function is continuous. Nevertheless, the convergence is not uniform. Why? Because
So I want to prove that Fn does not converge to 0 uniformly on 0, 1. Why? Because uniform convergence to 0 is equivalent to supremacy 0, 1, 0, 1, Fn of x tends to 0 as n tends to infinity. I mentioned it during the very first section about uniform continuity. Uniform convergence, sorry. So we need to understand what's about supremacy. Fn are continuous, so in fact we replace here supremum by maximum. And we need to investigate our function Fn. So to determine where is maximum value. So we look at Fn prime. What is Fn prime? N squared 1 minus x squared power n minus n squared x times n 1 minus x squared power n minus 1 times minus root times 2x. So what is it? That is 1 n squared 1 minus x squared power n minus 1 times 1 minus x squared minus 2n x squared. So Fn prime equals to 0 is equivalent to x equals to what? 1 over square root of 2n plus 1. And in fact, that is a maximum point. I have no time to draw a picture for signs of derivative. So what is about maximum? So maximum for x in 0, 1 Fn of x equals to Fn of 1 over square root of 2n plus 1. And let us substitute n squared times 1 over square root of 2n plus 1. And what we have here, 1 minus 1 over 2n plus 1 power n. Okay, so to recognize immediately what is it, that is 2n over plus 1 over. So what is it? That is 2n over 2n plus 1. I want to take a reciprocal, and it means 2n plus 1 over 2n, 1 plus 1 over 2n power n. And we know, I'll put here 2n and square root. 1 plus 1 over 2n power 2n tends to e, number e. So this tends to 1 over square root of e, and this number tends to infinity, right? So it means that tends to infinity. It means that that is not true. Hence, the sequence does not converge uniform, although the limiting function is identically 0. By the way, I'll use this example during the next lecture. Look, same is true when we'll replace n squared by squared, right?
It's again replace here, same, right? The same thing is valid also for the choice of n instead of n squared. During the next lecture, I'll continue this example. Okay. That's all for today. Thank you.